This is a video from section 2.4. Let f be a function defined on some open interval that contains the number a, except possibly at a itself. We say that the limit of f of x as x approaches a is L, written in this form, right? So this is the way we express that. If for every epsilon greater than 0, there exists a number delta greater than 0 such that if 0 is less than the absolute value of x minus a, which is less than delta, then the absolute value of f of x minus L is less than epsilon. And so we want the absolute value of x minus a to be greater than 0 because we don't want x to be a. Remember, we're looking for the values of x as they get close to a. Now, if the absolute value of x minus a is less than delta, then what that tells me is that negative delta is less than x minus a, which is less than delta. And if I add a to all three sides, what that says is x is between a minus delta and a plus delta. And so if 0 is less than the absolute value of x minus a, which is less than delta, then x is between a minus delta and a plus delta, and you just add the condition that you don't want x to be a. And then by the same token, the absolute value of f of x minus L is less than epsilon. Well, that means f of x is between L minus epsilon and L plus epsilon. So that's how that works there. And so I want to show you graphically what we're doing. Now, here's L, okay? And we're given some epsilon neighborhood around L, all right? Now, what that says is, given any epsilon greater than 0, so given any epsilon neighborhood around L, I can find a delta neighborhood around A, okay? And by the way, that delta depends on your choice of epsilon. So delta depends on epsilon. So I can find a delta neighborhood around A such that if X is in the delta neighborhood around A, then I claim that f of x will be within the epsilon neighborhood around L. And that right there is the epsilon delta definition of a limit. And so we're going to prove the statement using the epsilon delta definition. And we're going to start off with example 1. And example 1 says the limit as x goes to 5 of 3 halves x minus 1/2, we're going to prove that that equals 7. Now, we have some preliminary work here. This is how the book uses it, and I like how they do it, so we'll do it that way. So here's the preliminary work, and the preliminary work is guessing a value of delta. So in other words, we're trying to figure out a delta that works. Now, so we're given epsilon greater than 0. Let me write that again. So we're given epsilon greater than 0. We want to find a delta positive such that if 0 is less than the absolute value of x minus 5, which is less than delta, then the absolute value of 3 halves x minus 1/2 minus 7 is less than epsilon. 3 halves x minus 1/2, and then we're going to subtract 7, and that is going to be less than epsilon. But, so I'm going to say, but 3 halves x minus a half minus 7. Now, the comment I'm going to make here is I'm wondering if it's possible to rewrite that in terms of x minus 5 in absolute value, because the absolute value of x minus 5 is something that we know about. Now, this is equal to the absolute value of 3 halves x minus 15 over 2, but this is 3 halves times the absolute value of x minus 5. And so what does that say? We want a delta greater than 0 such that if 0 is less than the absolute value of x minus 5, which is less than delta, then 3 halves times x minus 5 is less than epsilon. Now, in other words, if 0 is less than the absolute value of x minus 5, which is less than delta, then what I'm going to do is I'm going to multiply both sides by 2/3. And so that says that x minus 5 in absolute value is less than 2/3 epsilon. And so what this suggests that I choose delta equal to 2/3 epsilon. And now we're ready for the proof. So let's look at the proof. Given epsilon greater than 0, we need to find a delta, okay? So I'm going to choose delta. We just need one that works. So I'm going to choose it to be 2/3 epsilon. If 0 is less than the absolute value of x minus 5, which is less than delta, then I'm going to take 3 halves x minus a half, and I'm going to subtract 7. But this is 3 halves x minus 15 over 2. Okay? Now, 3 halves x minus 15 over 2 is 3 halves times the absolute value of x minus 5. But that's less than, remember, well, here, I'm going to write 3 halves delta because that's what we're given. But remember that delta is 2/3 epsilon. And so this is 3 halves times 2/3 epsilon, which is equal to epsilon. So thus, if 0 is less than x minus 5, which is less than delta, excuse me, that should say delta, then the absolute value of 3 halves x minus a half minus 7 is less than epsilon. And so we have shown the limit as x goes to 5 of 3 halves x minus a half. I don't need absolute values here. So the limit as x goes to 5 of 3 halves x minus a half is indeed 7. And what I want to do is I want to look at a second example here. Suppose I give you this one. Suppose I had the limit as x goes to, we'll say 4, of x squared minus 2x minus 8 divided by x minus 4 is equal to 6. And so we're going to go ahead and look at our preliminary work. So given epsilon greater than 0, we want to find a delta positive such that if 0 is less than the absolute value of x minus 4, which is less than delta, then the absolute value of x squared minus 2x minus 8 divided by x minus 4 minus 6 is less than epsilon. So, but if I take the absolute value, this is x squared minus 2x minus 8 divided by x minus 4 minus 6. This is x minus 4 times x plus 2 divided by x minus 4 minus 6. So remember, what I'm trying to do is rewrite this expression in terms of x minus 4 in absolute value, because that's what I know about, right? And I want you to notice how the x minus 4's cancel. Why? Because I don't have to worry about x equaling 4. This condition guarantees that x can't be 4. And so this is the absolute value of x plus 2 minus 6, which is equal to x minus 4. And we're ready. So what that says is we want a delta positive such that if 0 is less than x minus 4, which is less than delta, then the absolute value of x minus 4 is less than epsilon. So this suggests we choose delta equal to epsilon. That's the suggestion. So now we're ready for the proof. Given epsilon greater than 0, choose delta to be epsilon. If 0 is less than x minus 4, which is less than delta, then the absolute value of x squared minus 2x minus 8 divided by x minus 4 minus, minus 6 is equal to the absolute value of x minus 4 times x plus 2 divided by x minus 4 minus 6, right? But the x minus 4's cancel. And so basically I'm going through the algebra again. This is the absolute value of x plus 2 minus 6, right? And so if we go to the next page the absolute value of x plus 2 minus 6 is the absolute value of x minus 4, which is less than delta, which is equal to epsilon. Thus, if 0 is less than x minus 4, which is less than delta, then the absolute value of x squared plus 2x minus 8 divided by x minus 4 minus 6 is less than epsilon. And we have thus shown that the limit as x goes to 4 of x squared plus 2x minus 8 divided by x minus 4 is equal to 6. And I want to do one more example for this video. And we're going to look at, we'll call this number 3. And it's from the book. So I'm just going to turn to the book here. And we'll call this example 3. Suppose I had the limit as x goes to 0 of x cubed equals 0. And so again, we have preliminary. Given epsilon greater than 0, we want to find a delta positive such that if the absolute value of x minus 0, oh, excuse me, here, let's write it this way. Let's write it on the next line. If the absolute value of x minus 0 is greater than 0 and less than delta, then the absolute value of x cubed minus 0 is less than epsilon. Now, if I take the absolute value of x cubed minus 0, this is equal to the absolute value of x cubed. But from the properties of absolute values, I could write this as the absolute value of x to the third. Remember, the goal is you want to be able to write this in terms of the absolute value of x minus 0. Okay? Now, the absolute value of x to the third is the absolute value of x minus 0 to the third. Now, what this says is, if the absolute value of x minus 0 is less than delta and greater than 0, then the absolute value of x, I'll say the absolute value of x cubed minus 0 is less than epsilon. But what that says is, if 0 is less than x minus 0 is less than delta, then the absolute value of x minus 0 to the third, right, is less than epsilon. And this actually gives us a suggestion on what we should choose. So we should choose delta to be, so basically what I'm going to do is I'm going to take the cube root of both sides. So I'm going to call this the cube root of epsilon, because I want you to watch what happens. So given epsilon greater than 0, choose delta, to be the cube root of epsilon. So whenever 0 is less than the absolute value of x minus 0 is less than delta, then the absolute value of x cubed minus 0 is the absolute value of x cubed, which is the absolute value of x to the third, which is the absolute value of x minus 0 to the third. Okay? But this is less than delta cubed. But remember that delta is the cube root of epsilon. So this is equal to the cube root of epsilon to the third, which is equal to epsilon. And so therefore, if 0 is less than x minus 0 is less than delta, then the absolute value of x cubed minus 0 is less than epsilon. And we have thus shown that the limit as x goes to 0 of x cubed ends up being 0. And that'll conclude this video for section 2.4. And I explained the limit definition formally, and we did 3 examples. Thank you.